At this point in your statistical education, you should already know about deviation from the mean. When we build linear regression models, there are two additional types of deviations we need to know about. So that is what I'm going to present in this video. Consider the horsepower of 32 model year 1973 and 74 automobiles. Horsepower varies among these automobiles, so it is a variable. Here's a graph illustrating this variation. One measure of center of this distribution of scores is the mean, which in this case is 147 horsepower. In this graph, I have plotted a line for the mean. Horsepower is plotted in the vertical direction, so this horizontal line is located at 147 on the horsepower scale. A deviation from the mean is simply a distance from the mean, so this line helps us identify the deviations for this set of scores. Some of the points are near the line so that they have small deviations. Others are some distance away with larger deviations. Let's pick one of these points. How about this one? This is an automobile that has 264 horsepower. The deviation from the mean is 264 minus 147, which is 117 horsepower. That is, this automobile has 117 more horsepower than the average of this set of automobiles. Now, what if we attempt to explain deviations by modeling horsepower as a function of engine size? You probably believe that the bigger the engine size, the more horsepower the automobiles will have, and that belief is supported by this graph. It therefore seems reasonable to suggest that automobiles with big engines will have more horsepower, and thus will be above the mean horsepower. In other words, the automobiles with the largest engines should have the largest positive deviations. Conversely, the automobiles with the smallest engines should have the largest negative deviations. Here is that same automobile, the one with 264 horsepower. We now have some additional information. We know the size of the engine. It is 351 cubic inches. If I create a linear model by regressing horsepower on engine displacement, I can predict the horsepower for a car with an engine that is 351 cubic inches. It is illustrated by this spot right here on my regression line. That point has a displacement value of 351 cubic inches and a power value of 199 horsepower. The value of 199 is greater than the mean value of 147, so we're predicting a positive deviation from the mean for a car with this size engine. Yet look at the car we are studying. It is indeed above the mean, but it is even further above the mean than we predicted. The actual horsepower of this automobile deviates from the predicted horsepower. This deviation is 264 minus 199, which is 65 horsepower. This automobile has 65 more horsepower than we would have expected for a car with this size engine. We did expect a deviation above the mean. In fact, we expected that to be the predicted value of 199 minus the mean of 147 for a deviation of 52 above the mean. A way to look at this is that we can explain why this car has 52 more horsepower than the average of these cars. That's because of the large engine size. But we cannot explain why this car has 65 more horsepower than the predicted value of 199. You should notice that I have been talking about two additional types of deviation. The deviation that we expected, based upon the value of the explanatory variable, engine size, and an additional deviation that we did not expect, This is the deviation of our observation from the regression line. Recall that the deviation from the mean of this car's horsepower is 117. You might notice that if we add up the deviation that we expected, 52, and the additional deviation from the regression line that we did not expect, 65, that this equals 117, the deviation from the mean. Each of these three types of deviations have a name. We call the deviation from the mean the total deviation. We call it total because the other two deviations add up to equal this deviation. The total deviation is the difference between a score and the mean. Model deviation is the difference between the predicted score and the mean. This is the deviation we expect when we model a response variable from an explanatory variable. The part we do not expect is the error deviation. This is the difference between our observed score and the predicted score, where the prediction comes from our linear regression model. The model deviation and error deviation are sometimes referred to by different names. The model deviation is sometimes called the explained deviation because it is the portion of the total deviation that we can explain with our model. The error deviation is sometimes called the unexplained deviation because it is not explained by our model. Perhaps the most common name for error deviation is residual deviation, or simply residual. Here's a picture putting it all together with the focus on a single observation. In this case, there's a negative relationship because the regression line is sloping downward from left to right. The observed value of the response variable deviates from the mean. That's the total deviation. Once we bring an explanatory variable into the picture to help explain the variability in our response variable, we can partition the total deviation into two parts. One part is the amount of the total deviation that we can explain with a linear model. It is the deviation that we predict with our model. But then there's the remaining deviation. That's the part we cannot explain. It is the residual. As we will see, dividing deviation from the mean into parts helps us better understand our models, the strength of the relationship of the explanatory and response variables, and observations of individual units.